Hey guys, welcome back to another RASK maths video, and in this video I'm going to be giving you guys a quick visual proof of a small angle sine approximation, i.e. as theta gets small, this can also be written as theta approaches 0, but you have to remember that theta isn't 0, so that's what you remember. As theta approaches 0, sine theta approaches just theta. This is the small angle approximation, and it's really useful. Now, the usual proof given is by expanding out the Taylor series of sine x, and then, the Maclaurin series, and then eliminating all terms with a power greater than 2 or 1, since the power of 2 is actually non-existent. It's got a coefficient of 0 in the sine Maclaurin series. So that's the general way of proving it, but I'm going to show you guys an interesting visual proof of it. So what we need to consider is, let's just think about a circle. And within this circle, we have a sector and a triangle, which is bounded by two radii of angle theta between them. Okay, and our goal is to work out what this shaded area is. So what we can do is first we can work out the area of this entire sector. Let me write this here. Area of the sector is going to be equal to, well, let's just say theta is in radians for now, and I'll show you what happens in degrees later. So theta is in radians, so therefore we get the area of this sector is just 1/2 theta r squared for any r. This is the general formula for the area of a sector. It comes from the fact that the area is actually given by theta over 2 pi multiplied by pi r squared, and then these cancel out and we're just left with our result. So there's our area of the sector. Now let's work out the area of this triangle, and I'll use a different color. Actually, no, I'll just use that again. So yeah, the area of this triangle, let's write it as a triangle, is going to be equal to, well, here we can just use the formula 1/2 AB sine C, or, so in this case, for the area of the triangle, that's just going to be 1/2 r squared sine theta, like so. And now what we can do is, well, to work out the area of the shaded portion, we just have to subtract the area of the sector and the area of the triangle. So it's going to be, I'm going to say a sector minus a triangle, and that's equal to 1/2, I'm going to put the r squared theta minus 1/2 r squared sine theta. Okay, so I'm going to call this value the area of the shaded, and that's equal to this. And what I'm going to do is factor out the 1/2 r squared, so we're just left with theta minus sine theta. Now what you can see is, as this angle theta goes to 0, this shaded bit is going to go to 0 as well. I think that's fairly obvious. Let me show you an example. So for a really big radius, so for a really big angle like this is what we're going to get, and our shaded area is going to be quite substantial. But if we have a really tiny radius, I keep saying radius, if we have a really tiny angle, then our shaded area is going to just be this tiny bit there. And you can see as it gets smaller and smaller, the shaded bit is just going to disappear as it gets closer and closer to a real triangle. So what that basically says mathematically is, as theta approaches 0 or gets small, the area of the shaded region also approaches 0. Now obviously, since 1/2 r squared is a constant, that must mean theta minus sine theta approaches 0 as theta approaches 0. And therefore, we've proved as theta gets really small, theta approaches sine theta. Now the approach sign is a bit weird. You can also write it as sine theta approaches theta. It means the same thing. But yeah, so there's our proof. Theta approaches sine theta as theta approaches 0. if that makes sense. So what this is saying is it's not actually approaching 0, it's just getting really small. And as it gets small, it starts to approach sine theta. Now, let me show you what happened if we were to do this in degrees. So if we were to say theta in degrees, we would get our area of the sector would now be theta over 360 multiplied by pi r squared. The triangle area is the same because sine function already has it in. Doesn't really change, if that makes sense. So area of the triangle is just going to be 1/2 sine theta, working in degrees. And this gives us area of the shaded is going to be, sorry, it's meant to be 1/2 r squared, is going to be 1/2 r squared. Now let me factor out I'm going to have theta pi over 180 minus sine theta. And as you can see, it's still going to approach 0 as theta gets small. But this doesn't leave us with the same result, because now we get theta pi over 180 approaches sine theta. And hopefully you can see the problem here. If we're in degrees, then sine theta is still taken as sort of radian-like argument, whereas what we used to calculate our angle fraction was now converted into degrees. So we end up with the degree radian conversion, pi over 180, multiplied by this additional, multiplied by theta, which is the difference, right? Because degrees, essentially, they're a lot bigger than radians, so we need to scale them back down. And yeah, this is the formula if you're working in degrees for the small angle. So quick side note there, but there we go. So that's a quick visual proof of the sine small angle approximation. Hopefully you liked that, and see you guys in future tutorial. Bye.